Prog plug. FOC bypass valve. FMU 2.5 bleed valve. TAC valve. NOC valve. MAVS VTCC valves. INOC valve. Sensors 2.9 bleed valve. BU general lock valve. NAC zone vent valve. Figure 2-56. Systems controlled by EC. Each channel of the EC has 7 electrical connections, 3 on each side and 1 on the bottom. Both channels share the inputs of the 2 connections on the top of the EC. These are the programming plug and test connector. The programming plug selects the proper software in the EC for the thrust rating of the engine. The plug attaches to the engine fan case with a lanyard. When removing the EC, the plug remains with the engine. Each channel of the EC has 3 pneumatic connections on the bottom of the EC. Transducers inside the EEC supply the related and opposite EEC channel with a signal in proportion to the pressure. The pressures that are read by the EEC are ambient pressure, burner pressure, LPC exit pressure, and fan inlet pressure. Each channel has its own wire color that connects the EEC to its sensors. Channel A wiring is blue, and channel B sensor signals are green. The non-EEC circuit wire is gray, while the thermocouple signals are yellow. This color coding helps simplify which sensors are used with each channel. Fuel system operation. The fuel pump receives fuel from the airplane fuel system. The low-pressure boost stage of the pump pressurizes the fuel and sends it to the fuel/oil cooler, FOC. The fuel flows from the FOC through the fuel pump filter element, and then to the high-pressure main stage of the pump. The high-pressure main stage increases the fuel pressure and sends it to the fuel metering unit, FMU. It also supplies servo fuel to the servo fuel heater and engine components. Fuel for combustion, metered fuel, goes through the fuel flow transmitter to the distribution valve. Figure 2-57. The fuel distribution valve supplies metered fuel to the fuel supply manifolds. Figure 2-58. The fuel injectors get the metered fuel from the fuel supply manifolds and spray the fuel into the engine for combustion. Figure 2-59. The fuel pump housing contains a disposable fuel filter element. The fuel filter differential. Figure 2-57. Fuel flow transmitter. Figure 2-58. Fuel distribution valve. 2-41. Figure 2-59. Fuel manifolds. Pressure switch supplies a signal to the EC that indicates an almost clogged filter condition. Unfiltered fuel can then bypass the filter element if the element becomes clogged. Water injection system. On warm days, thrust is reduced because of the decrease in air density. This can be compensated for by injecting water at the compressor inlet or diffuser case. This lowers the air temperature and increases air density. A microswitch in the fuel control is actuated by the control shaft when the power lever is moved toward the maximum power position. A water injection speed reset servo resets the speed adjustment to a higher value during water injection. Without this adjustment, the fuel control would decrease RPM, so that no additional thrust would be realized during water injection. The servo is a shuttle valve that is acted upon by water pressure during water injection. Movement of the servo displaces a lever on the chem-operated lever linkage to the speed governor speeder spring, increasing the force of the speeder spring and increasing the set speed. Because the resulting RPM is usually higher while water is flowing, increased thrust during water injection is ensured. If the water injection system is not armed in the cockpit, or if there is no water available, nothing happens when the water injection switch in the fuel control unit is actuated. When water is available, a portion of it is directed to the water injection speed reset servo. Water injection systems are not normally used on high-bypass turbofan engines. Fuel control maintenance. The field repair of the turbine engine fuel control is very limited. The only repairs permitted in the field are the replacement of the control and adjustments afterwards. These adjustments are limited to the idle RPM and the maximum speed adjustment, commonly called trimming the engine. Both adjustments are made in the normal range of operation. During engine trimming, the fuel control is checked for idle RPM, maximum RPM, acceleration, and deceleration. The procedures used to check the fuel control vary depending on the aircraft and engine installation. The engine is trimmed in accordance with the procedures in the maintenance or overhaul manual for a particular engine. In general, the procedure consists of obtaining the ambient air temperature and the field barometric pressure, not sea level, immediately preceding the trimming of the engine. Care must be taken to obtain a true temperature reading comparable to that of the air that enters the engine. Using these readings, the desired turbine discharge pressure or EPR, engine pressure ratio, reading is computed from charts published in the maintenance manual. The engine is operated at full throttle, or at the part power control trim stop, for a sufficient period of time to ensure that it has completely stabilized. 5 minutes is the usual recommended stabilization period. A check should be made to ensure that the compressor air bleed valves have fully closed and that all accessory drive air bleed for which the trim curve has not been corrected, such as a cabin air conditioning unit, has been turned off. When the engine has stabilized, a comparison is made of the observed and the computed turbine discharge pressure PT7, or EPR, to determine the approximate amount of trimming required. If a trim is necessary, the engine fuel control is then adjusted to obtain the target turbine discharge pressure PT7 or EPR on the gauge. Immediately following the fuel control adjustment, the tachometer reading is observed and recorded. Fuel flow and exhaust gas temperature readings should also be taken. On Pratt & Whitney engines, using a dual spool compressor, the observed N2 tachometer reading is next corrected for speed bias by means of temperature/RPM curve. The observed tachometer reading is divided by the percent trim speed obtained from the curve. The result is the new engine trim speed in percent, corrected to standard day, 59 degrees Fahrenheit or 15 degrees Celsius, temperature. The new trim speed in RPM may be calculated when the RPM at which the tachometer reads 100% is known. This value may be obtained from the appropriate engine manual. If all these procedures have been performed satisfactorily, the engine has been properly trimmed. Engine trimming should always be carried out under precisely controlled conditions with the aircraft headed into the wind. Precise control is necessary to ensure maintenance of a minimum thrust level upon which the aircraft performance is based. In addition, precise control of engine trimming contributes to better engine life in terms of both maximum time between overhaul and minimum out of commission. 2-42. Time due to engine maintenance requirements. Engines should never be trimmed if icing conditions exist. Most electronic fuel control systems do not require trimming or mechanical adjustments. Changes to the EEC in the FADEC system is normally accomplished through software changes, or changing the EEC. Engine fuel system components. Main fuel pumps, engine-driven. Main fuel pumps deliver a continuous supply of fuel at the proper pressure, and at all times during operation of the aircraft engine. The engine-driven fuel pump must be capable of delivering the maximum needed flow at appropriate pressure to obtain satisfactory nozzle spray and accurate fuel regulation. These engine-driven fuel pumps may be divided into two distinct system categories. 1. Constant displacement. 2. Non-constant displacement. Their use depends on where in the engine fuel system they are used. Generally, a non-positive displacement, centrifugal pump, is used at the inlet of the engine-driven pump to provide positive flow to the second stage of the pump. The output of a centrifugal pump can be varied as needed and is sometimes referred to as a boost stage of the engine-driven pump. The second or main stage of the engine-driven fuel pump for turbine engines is generally a positive displacement type of pump. The term positive displacement means that the gear supplies a fixed quantity of fuel to the engine for every revolution of the pump gears. Gear-type pumps have approximately straight-line flow characteristics, whereas fuel requirements fluctuate with flight or ambient air conditions. Hence, a pump of adequate capacity at all engine operating conditions has excess capacity over most of the range of operation. This is the characteristic that requires the use of a pressure relief valve for bypassing excess fuel back to the inlet. A typical two-stage turbine engine-driven pump is illustrated in Figure 2-60. The impeller, which is driven at a greater speed than the high-pressure elements, increases the fuel pressure depending upon engine speed. The fuel is discharged from the boost element, impeller, to the two high-pressure gear elements. A relief valve is incorporated in the discharge port of the pump. This valve opens at a predetermined pressure, and is capable of bypassing the total fuel flow. This allows fuel in excess of that required for engine operation at the time to be recirculated. The bypass. Figure 2-60. Dual-element fuel pump. Fuel is routed to the inlet side of the second stage pump. Fuel flows from the pump to the fuel metering unit or fuel control. The fuel control is often attached to the fuel pump. The fuel pump is also lubricated by the fuel passing through the pump, and it should never be turned without fuel flow supplied to the inlet of the pump. As the engine coasts down at shutdown, the fuel pump should be provided with fuel until it comes to a stop. Fuel heater. Gas turbine engine fuel systems are very susceptible to the formation of ice in the fuel filters. When the fuel in the aircraft fuel tanks cools to 32 degrees Fahrenheit or below, residual water in the fuel tends to freeze, forming ice crystals. When these ice crystals in the fuel become trapped in the filter, they block fuel flow to the engine, which causes a very serious problem. To prevent this problem, the fuel is kept at a temperature above freezing. Warmer fuel also can improve combustion, so some means of regulating the fuel temperature is needed. One method of regulating fuel temperature is to use a fuel heater which operates as a heat exchanger to warm the fuel. The heater can use engine bleed air or engine lubricating oil as a source of heat. The bleed air type is called an air-to-liquid exchanger and the oil type is known as a liquid-to-liquid heat exchanger. The function of a fuel heater is to protect the engine fuel system from ice formation. However, should ice form in the filter, the heater can also be used to thaw ice on the fuel screen to allow fuel to flow freely again. On most installations, the fuel filter is fitted with a pressure drop warning switch, which illuminates a warning light on the cockpit instrument panel. If ice begins to collect on the filter surface, the pressure across the filter slowly decreases. When the pressure reaches a predetermined value, the warning light alerts the flight deck personnel. 2-43. Fuel de-essing systems are designed to be used intermittently. The control of the system may be manual, by a switch in the cockpit, or automatic, using a thermostatic sensing element in the fuel heater to open or close the air or oil shutoff valve. A fuel heater system is shown in Figure 2-61. In a FADEC system, the computer controls the fuel temperature by sensing the fuel temperature, and heating it as needed. Fuel filters. A low-pressure filter is installed between the supply tanks and the engine fuel system to protect the engine-driven fuel pump and various control devices. An additional high-pressure fuel filter is installed between the fuel pump and the fuel control to protect the fuel control from contaminants that could come from the low-pressure pump. The three most common types of filters in use are the micron filter, the wafer screen filter, and the plain screen mesh filter. The individual use of each of these filters is dictated by the filtering treatment required at a particular location. The micron filter has the greatest filtering action of any present-day filter type and, as the name implies, is rated in microns. Figure 2-62. A micron is 1/1000th of 1 millimeter. The porous cellulose material frequently used in construction of the filter cartridges is capable of removing foreign matter measuring from 10-25 microns. The minute openings make this type of filter susceptible to clogging. Therefore, a bypass valve is a necessary safety factor. Relief valve. Filter element. Inlet. Baffle. Outlet. Drain cock. Figure 2-62. Aircraft fuel filter. Since the micron filter does such a thorough job of removing foreign matter, it is especially valuable between the fuel tank and engine. The cellulose material also absorbs water, preventing it from passing through the pumps. If water does seep through the filter, which happens occasionally when filter elements become saturated with water, the water can and does quickly damage the working elements of the fuel pump. Air baffle fuel tubes. Fuel inlet. Fuel outlet. Air outlet. Fuel temperature sensor air inlet. Cooling fins. Air shutoff valve. Figure 2-61. Fuel heater. 2-44. And control units. Since these elements depend solely on the fuel for their lubrication. To reduce water damage to pumps and control units, periodic servicing and replacement of filter elements is imperative. Daily draining of fuel tank sumps and low-pressure filters eliminates much filter trouble and undue maintenance of pumps and fuel control units. The most widely used filters are the 200 mesh and the 35 mesh micron filters. They are used in fuel pumps, fuel controls, and between the fuel pump and fuel control, where removal of micronic particles is needed. These filters, usually made of fine mesh steel wire, are a series of layers of wire. The wafer screen type of filter has a replaceable element, which is made of layers of screen discs of bronze, brass, steel, or similar material. Figure 2-63. This type of filter is capable of removing micronic particles. It also has the strength to withstand high pressure. Fuel spray nozzles and fuel manifolds. Although fuel spray nozzles are an integral part of the fuel system, their design is closely related to the type of combustion chamber in which they are installed. The fuel nozzles inject fuel into the combustion area in a highly atomized, precisely patterned spray so that burning is completed evenly, in the shortest possible time, and in the smallest possible space. It is very important that the fuel be evenly distributed and well centered in the flame area within the liners. This is to preclude the formation of any hot spots in the combustion chambers, and to prevent the flame burning through the liner. Fuel nozzle types vary considerably between engines, although for the most part fuel is sprayed into the combustion area under pressure through small orifices in the nozzles. The two types of fuel nozzles generally used are the Simplex and the duplex configurations. The duplex nozzle usually requires a dual manifold and a pressurizing valve or flow divider for dividing primary and secondary main fuel flow, but the Simplex nozzle requires only a single manifold for proper fuel delivery. The fuel nozzles can be constructed to be installed in various ways. The two methods used quite frequently are 1. External mounting, wherein a mounting pad is provided for attachment of the nozzles to the case or the inlet air elbow, with the nozzle near the dome. Or 2. Internal mounting at the liner dome, in which the chamber cover must be removed for replacement or maintenance of the nozzle. The nozzles used in a specific engine should be matched so that they flow equal amounts of fuel. Even fuel distribution is important to efficient combustion in the burner section. The fuel nozzle must present a fine spray with the correct pattern and optimum atomization. Simplex fuel nozzle. The Simplex fuel nozzle was the first nozzle type used in turbine engines, and was replaced in most installations with the duplex nozzle, which gave better atomization at starting and idling speeds. The Simplex nozzle is still being used. Human hair is about 100 microns in diameter. 25,400 microns equals 1 inch. Spacer. Filter sump. Filter head. O-ring filter disc. Figure 2-63. Wafer screen filter. 2-45. In several installations. Figure 2-64. Each of the Simplex nozzles consists of a nozzle tip, an insert, and a strainer made up of fine mesh screen and a support. Figure 2-64. Simplex air blast nozzle cutaway. Duplex fuel nozzle. The duplex fuel nozzle is widely used in present-day gas turbine engines. As mentioned previously, its use requires a flow divider. But at the same time it offers a desirable spray pattern for combustion over a wide range of operating pressures. Figure 2-65. A nozzle typical of this type is illustrated in Figure 2-66. Air blast nozzles. Air blast nozzles are used to provide improved mixing of the fuel and airflow to provide optimum spray for combustion, as can be seen in Figure 2-64. Squirrel vanes are used to mix the air and fuel at the nozzle opening. By using a proportion of the primary combustion airflow in the fuel spray, locally rich fuel concentrations can be reduced. This type of fuel nozzle. Primary only. Primary and main. Figure 2-65. Duplex nozzle spray pattern. Can be either simplex or duplex, depending upon the engine. This nozzle type can operate at lower working pressures than other nozzles, which allows for lighter pumps. This air blast nozzle also helps in reducing the tendency of the nozzle to carbon up, which can disturb the flow pattern. Flow divider. A flow divider creates primary and secondary fuel supplies that are discharged through separate manifolds, providing two separate fuel flows. Figure 2-67, metered fuel from the fuel control enters the inlet of the flow divider and passes through an orifice, and then onto the primary nozzles. A passage in the flow divider directs fuel flow from both sides of the orifice to a chamber. This chamber contains a differential pressure bellows, a viscosity compensated restrictor, VCR, and a surge dampener. During engine start, fuel pressure is applied to the inlet port, and across the VCR, surge dampener, and onto the primary side of the nozzles. Fuel is also applied under pressure to the outside of the flow divider bellows, and through the surge dampener to the inside of the flow divider bellows. This unequal pressure causes the flow divider valve to remain closed. When fuel flow increases, the differential pressure on the bellows also increases. At a predetermined pressure, the bellows compresses, allowing the flow divider valve to open. This action starts fuel flow to the secondary manifold, which increases the fuel flow to the engine. This fuel flows out of the secondary opening in the nozzles. Fuel pressurizing and dump valves. The fuel pressurizing valve is usually required on engines incorporating duplex fuel nozzles to divide the flow into 2-46. Screen. Fuel inlet port. Small slot, large slot compressor discharge air. Flow divider valve. Spin chamber. Fuel discharge orifice. Figure 2-66. Duplex fuel nozzle. Figure 2-67. Flow divider. Primary and secondary manifolds. At the fuel flows required for starting and altitude idling, all the fuel passes through the primary line. As the fuel flow increases, the valve begins to open the main line until at maximum flow the secondary line is passing approximately 90% of the fuel. Fuel pressurizing valves usually trap fuel forward of the manifold, giving a positive cutoff. This cutoff prevents fuel from dribbling into the manifold and through the fuel nozzles, limiting after fires and carbonization of the fuel nozzles. Carbonization occurs because combustion chamber temperatures are lowered and the fuel is not completely burned. A flow divider performs essentially the same function as a pressurizing valve. It is used, as the name implies, to divide flow to the duplex fuel nozzles. It is not unusual for units performing identical functions to have different nomenclature between engine manufacturers. Combustion drain valves. The drain valves are units used for draining fuel from the various components of the engine where accumulated fuel is most likely to present operating problems. The possibility of combustion chamber accumulation with the resultant fire hazard is one problem. A residual problem is the deposit of lead and orgum, after evaporation, in such places as fuel manifolds and fuel nozzles. In some instances, the fuel manifolds are drained by an individual unit known as a drip or dump valve. This type of valve may operate by pressure differential, or it may be solenoid operated. The combustion chamber drain valve drains fuel that accumulates in the combustion chamber after each shutdown and fuel that may have accumulated during a false start. If the combustion chambers are the can type, fuel drains by gravity down through the flame tubes or interconnector tubes until it gathers in the lower chambers, which are fitted with drain lines to the drain valve. If the combustion chamber is of the basket or annular type, the fuel merely drains through the air holes in the liner and accumulates in a trap in the bottom of the chamber housing, which is connected to the drain line. 2-47. After the fuel accumulates in the bottom of the combustion chamber or drain lines, the drain valve allows the fuel to be drained whenever pressure within the manifold or the burners has been reduced to near atmospheric pressure. A small spring holds the valve off its seat until pressure in the combustion chamber during operation overcomes the spring and closes the valve. The valve is closed during engine operation. It is imperative that this valve be in good working condition to drain accumulated fuel after each shutdown. Otherwise, a hot start during the next starting attempt or an afterfire after shutdown is likely to occur. Fuel quantity indicating units. Fuel quantity units vary from one installation to the next. A fuel counter or indicator, mounted on the instrument panel, is electrically connected to a flowmeter installed in the fuel line to the engine. The fuel counter, or totalizer, is used to keep record of fuel use. When the aircraft is serviced with fuel, the counter is manually set to the total number of pounds of fuel in all tanks. As fuel passes through the measuring element of the flowmeter, it sends electrical impulses to the fuel counter. These impulses actuate the fuel counter mechanism so that the number of pounds passing to the engine is subtracted from the original reading. Thus, the fuel counter continually shows the total quantity of fuel, in pounds, remaining in the aircraft. However, there are certain conditions that cause the fuel counter indication to be inaccurate. Any jettisoned fuel is indicated on the fuel counter as fuel still available for use. Any fuel that leaks from a tank or a fuel line upstream of the flowmeter is not counted. 2-48. Chapter 3.